So far in our class, we have focused on trying to understand a single variable within a population, such as what's the average income of people in San Francisco, what is the average height, or what is the proportion of people that have had COVID. Right? Now, with regression analysis, we're trying to understand the relationship between two or more variables. So let's say, what's the relationship between income and education, or what's the relationship between diet and health, right, and so on, right? And now, in order for us to understand this, or understand the technique in regression analysis, we have to rethink the way data is created a little bit. So, for example, in the previous chapter, right, we have simply, let's say we have an x, right? We have a xi equals, equals 200, equals 23. Okay, and so the way we used to think about where data comes from is, well, it comes from a population, right? Here's x, and then I really should say 1 or something. Yeah, it doesn't matter. It comes from a population, and say the population is distributed normally, okay, and it is centered at mu, right? And let's say the mu is, mu is 30. Okay, so where's 23 then? Well, 23 then is over here, right? So here's our x value that we observed, right? X1 of 23, right? 23 there. Okay, and that's how we used to think where data comes from. Right? And we don't think much, we don't think much else of it. However, with regression analysis, right, the way we're going to think about it is like so. It's like we want to think of that each observation is a yi, but that equals to the mu plus this epsilon term. Okay, so this is called epsilon. Right, and it means, and we're going to call this the error term. Okay, now it doesn't mean something's wrong with this. Okay? It just error term represents a deviation away from the mean. Right? And so instead of looking at this as a distribution assembly, things just exist, we're gonna say that this is a deviation. Right? And so each yi is an observation. Right? I say, for example, right, the average height here is 5'8", 5'9" Okay, so let's say that is the average height of everybody here in the Bay Area, and then your height is your height is 5'8". Right? Now, of course, right, some people are taller, some people are shorter, right? Everybody deviates away from this average, and so the way we will, here's your observation. Right? And the way we want to think about the 5'8" is not just as 5'8", but it's 5'8" is, right, 5'9", which is the mu, plus this deviation, which is -1 inches, which is the epsilon. Right? And so if you are 5'8", then the way we're not concerned with the fact that you're 5'8". We're concerned with the fact, or not concerned, sorry, interested in the fact that you are 1 inch below the average. Right? And if you are 5'10", then we would say, okay, then you are 1 inch above the average. And in regression analysis, our goal is to try to explain this deviation. Try to explain why individuals are deviating away from the mean. Right? And if everybody has the same height, right? If we live in a society having the same height, then we wouldn't need regression analysis. Then mu would just simply be able to explain everything. But everybody has different height, everybody has different health, different income, and so regression analysis is going to allow us to understand those deviation. Another way to kind of think about it, let me see if I have room here. I can draw a graph here. Right? Another way to think about this is you have mu here in the middle. So here again we have 5'9". All right, and so say the first person here 5'8". So the deviation is the distance away from the mean to this person. So here is epsilon. Okay, a second person, right, could have an epsilon that is positive. See, everything below epsilon is negative, a person here could be super tall, right? This is like what, 6 foot, like 6'10", right? And this person here, right, will have an epsilon that is greater than 0. Okay, and so everybody is deviating somewhere about the line. Now, if you are 5'9", then your epsilon will equal 0. Right? You will be then we will look at you as you're not deviating away from the mean. Okay, and when we develop a model, like a simple linear regression model, is we're trying to introduce variables that help us explain this deviation. Right? It could be genetics, could be diet, and whatever. Right? Okay, so that's what a model is. All right, a model is basically an assumption. Okay, so maybe let's write that down here. A model, right, is what we assume to be true. Right? We assume that, right, y and x has a relationship that can be expressed in this manner. Right? This is a linear. This is a linear relationship. Right? And so we assume this. We assume that there is a relationship out there between y and x, whatever these two variables is, that can be expressed in this manner. And every observation could be explained in this fashion. So first, let me draw a graph. Okay, so I draw a little x and y diagram here, and let's say that x is age, okay, and y is height. Right? Okay, and so we assume that there is a relationship between age and height. Okay, now hopefully, as you get older, you get taller, and so we have a linear relationship. And if we plot, if we have a sample, if we look at everybody in society, right, we'll probably see scattered around like so, right. And here we can pick. We can pick an age here. So let's say that is the age. This is 12-year-olds, right? Now you have some 12-year-olds that are really short, some 12 years old probably in the middle, and some 12-year-olds are really, really tall, right? And then we say, well, each point here then, right, is an observation. This every point is an yi. Right? And now, what does this linear mean? So we say that, well, there is a line, right? There is a line there's a line right in the middle that fits all the data here, and that is what we'll call a simple linear regression equation. So this line here is the b naught plus b beta 1 xi. Okay, and then so the deviation away from this middle here, that is your epsilon I. So every yi is the line b0 plus beta 0 plus beta 1 xi plus this epsilon I. Right? So this part here, that is the line, and it's how much you deviate away from the line. Right? So for anybody here, so this will be greater than 0, and this individual, right, is below the average. Right? So there will be this epsilon I will be less than 0. Right? Now another thing to say, right? So this we use the notation expected value. So this here, right, is the expected value given a fixed xi, right? So for example here, right, there's like this here, let's say that's a bunch of 18-year-olds, right? Then this point here, on the line, this will be the average height of the 18-year-olds. So let's say this point here, that will be the average height of 18-year-olds, or the expected height of 18-year-olds. Okay, so this is what we assume to be true, and this is what we assume that is out in nature, and this is the determinant of everybody's height, you and I, right? Everybody here. And notice that you are writing this in Greek letter. Beta is a Greek letter, so as usual, anything that's written with a Greek letter, it represents the population parameter. And so these are going to be the parameters that we are interested in measuring or trying to estimate, right? Because if we can figure out what beta 1 is, right, then we can figure out, well, for example, what in this context, beta 1 will represent how much taller each person get as they age 1 year, right? Because beta 1 is the slope of this line, right? All right. So that is our simple linear regression model.